In this video, we're going to look at why this Lagrange multiplier stuff works like we say it does. So let x be open in Rn, let fg be functions from x to R of class C1, let S be our level set of g at height C, and let f restricted to S be denoted as such. Then if f restricted to S has an extremum at x naught, then the gradient of g at x naught, or such that the gradient of g at x naught doesn't equal 0, then there must be a scalar lambda such that gradient of f of x naught equals the lambda times the gradient of g at x naught. So in this proof, we're just going to sketch the proof. The main idea is that the gradient of f and I'll write it specifically like this, the gradient of f at x naught and the gradient of g at x naught are both orthogonal to s at x naught. That's the key idea. And I'll note we already know that the gradient of the function is orthogonal to the level set. So we already know that the gradient of g of x naught is orthogonal, and I'll write that, to s at x naught. So we just need to show this for f of the gradient of f at x naught. And to do that, we're going to suppose x of t is a curve in S, so restricted to S, passing through x naught at t naught. And we're going to ask, what is the derivative of f composed with x of t, or with x at t naught? By the chain rule, this is the gradient of f of x of t naught dotted with x prime of t naught, which equals the gradient of f at x naught, because x naught is x of t naught, dotted with x prime of t naught. But also, t naught is a local extremum of the single variable function f composed with x. Because we noted that this is an extremum of f restricted to s. And this curve x is running around s, so it has to have a maximum or minimum or some sort of extremum at x naught. And this might not seem like a single variable function, but it is, because our input is just some variable t. It turns into a vector, and then we turn that vector back into a scalar, so that we have a function from R to R. So by single variable calculus, we know that where we have an extremum on an open set, that means that the derivative there has to be 0. So that means that dt of f circ x of t naught equals 0. Therefore, gradient of f of x naught dotted with x prime of t naught, which is a curve on S, equals 0. And since f is the gradient of f at x naught is orthogonal to really any curve passing through S at x naught, that's just what we had for this x prime here. Since it's orthogonal to the tangent line, we'd say, of any curve at t naught, this means that, that means that the gradient of f of x naught is orthogonal to S at x naught, which is exactly what we wanted to show. Since these are both orthogonal, and due to some dimensionality stuff, since these are both orthogonal, and we can say the hypersurface or the vector orthogonal to a hypersurface is unique up to scalar multiples. And orthogonal vectors to hypersurfaces are unique up to scalar multiple. I'm running out of room. Up to scalar multiples. We're good. That's a nice way to end a proof. It's worth noting if the gradient of g was 0, then clearly it's orthogonal. And clearly f would be orthogonal by what we just showed, but there's not necessarily a scalar you can multiply to g to get to f, because g would just be 0, so any scalar would be 0. So that's kind of why we have this gradient of g, because it's possible that, yes, they're both orthogonal, but the gradient of g is just 0, which is still orthogonal, but then multiplying by lambda will just still get you 0. So that's why we have that little exception in there, but other than that, there is your kind of sketchy proof for why this all works out. So there you go.